All tennis shots are either flat or contain some amount of spin. Spin can be categorized as either topspin, which causes the ball to kick up, or underspin, which causes it to die and move backwards after the bounce. Although the force applied on the tennis ball is the same, flat strokes tend to travel faster due to the fact that all the energy is converted into translational kinetic energy. Strokes with spin sacrifice this translational kinetic energy for rotational energy. Since we are optimizing the flight time for the tennis ball, we have selected flat strokes because they allow for the least hang time. For example, Robin Soderling, a tennis player, was capable of hitting speeds of over 90 miles per hour without any spin.
The optimal tennis shot is hit when the ball lands at about 22 meters away from the baseline, which is about here, and it takes about only 1 second to travel from one side to the other. To do this, we must have a distance equation, and to find that, we're going to start off with A is equal to dv over dt. And now we're going to find the velocity equation by performing separation of variables. So we get dv is equal to A times dt. And now we take the integral on both sides to get, so we have the integral from v0 to v of dv is equal to the integral from 0 to delta t of a dt, which is equivalent to v minus v0 is equal to a times delta t. And we add v0 on both sides to get the velocity equations. So therefore, v is equal to v0 plus a times delta t. And that's the velocity equation. Now to find the distance equation using the velocity equation. So we know velocity is equal to dx over dt. And we again perform separation of variables to get dx is equal to v times dt. And now we take the integral on both sides. So we have the integral from x0 to x of dx is equal to the integral of from 0 to delta t of v dt. We already found the equation of v, so we plug that in here. So we get the so the equation would become the integral from x0 to x of dx is equal to the integral from 0 to delta t of v0 plus 8t dt. And now we have to solve the integral. We'll solve the integral to get x minus x0 is equal to v0t plus half a t square. And now we add x0 on both sides to get the final distance equation. So x is equal to x0 plus v0t plus half a t square, and that's the distance equation. Now that we have the distance equation, we are going to find the correct speed and angle at which to hit this tennis shot. And as I said before, the optimal tennis shot is hit when the ball is 22 meters away, so delta x would be 22 meters. And the time is 1 second, so t is equal to 1 second. And the usual height of a tennis shot is about 1 meter, so h naught is 1 meter. So now all we have to do is plug in these three values in for their variables to find the value of v0. So when we plug that in, it would become 22 is equal to 1 plus v0 times 1 plus half times 9.8 times 1 squared. So we get v0 is equal to 16.1 meters per second. And that's the correct speed at which to hit this tennis shot. Now we have to find the angle such that the ball goes over the tennis net. So for that we're going to be using the Pythagoras theorem. So this is the value theta which we need to find, and the height of a tennis net is 1 meter, which is this. We can call this y, and the distance from where the shot is hit to the net would be The length of the tennis court divided by 2, which is 11.885 meters, which we'll call x. And so to find the value of theta, we can just do tan theta is equal to y over x, and theta is equal to the tan inverse of y over x. So once we solve that, we get theta is equal to 4.81. Therefore, the ball should be hit at 16.1 meters per second at an angle of 4.81 degrees to hit the optimal tennis shot.